Okay, so we want to look at correlation, we want to look at regression, we want to look at prediction, we want to look at performance, we want to look at feature importance. That's a lot of things to look at. Correlation, regression, prediction, performance, feature, performance. But largely, the class will border on correlation and some prediction characteristics as we go along. So, correlation. Really, what is correlation? I believe you know most of these things already, so perhaps it will be a stroll in the park. But largely, correlation measures the association between two variables, right? So it's looking at the magnitude, like the size, and then looking at the direction. The direction. So are the two going in same direction or they are going in opposite directions? Okay, so that's what correlation is doing. Now you see that there are so many examples of two things can be correlated, like randomly two things can just be correlated. For instance, age and then your eyesight. Age and then your eyesight. Now, do you think these two are correlated? They may have something in common because the more you grow, it's likely your vision would get a little worse, right? So they are associated. Running time and calories burnt. They could be associated that the more you run, you spend time in jogging, and it's more likely that you burn some calories also. Temperature and then say ice cream sales. Well, or let's say water sales. If the temperature of your water is pretty cold, especially when the weather is that hot, you would likely get more sales than if the temperature of the water say is warm. You see, people more likely don't want to purchase the water. So you can actually take data on your sales, the sales you make, and you take data on temperature. You test, you take data. So today, this is this number of bottles. This is the temperature. You just take. Then you run some correlation. You actually see if it is positive, that they go hand in hand, they both increase together. If you increase the temperature, will the sales increase? Or if the temperature goes down, will the sales go down? Or vice versa, if one goes up, will the other come down? Study time and then grades. Price and quantity demanded of normal goods. And these are very common things that you can test for the association for. When your price is going up, are you likely to demand more of a normal good? Economics has already proven that. Blood pressure and age. I mean, these are things that we know that they are correlated. Wage and experience. Stock price and risk. You could compute the risks, compute the stock prices for a commodity or the stock, and then just run a correlation matrix or the analysis and see what is the strength. Are they going in opposite direction or check the direction? Consumption and savings. When you are consuming, is it correlated with your savings? I believe for this one, it's pretty straightforward because if your income is 100 and you consume 80, savings will be 20. So you take consumption 80, savings 20 for this month. Next month, consumption 50, savings 50. Consumption maybe 65, savings maybe 35. You run a correlation. What do you think? Do you think it will be positive or negative between consumption and savings? Anybody, what do you think? Yes, Kingsford.
So I think it will be negative. If you consume more, you will save less.
Right, right, right. Thank you, Douglas, also. And so you would see that if you draw a scatter plot, if you should fit a scatter plot with any two of these variables, say consumption on the y-axis, and then savings on the x-axis, if you see that the data points seem to mimic this direction, then we would say that this data, or between consumption and savings, what kind of association is this? The first one. Is it positive or negative? Anybody?
Positive.
Yes, so positive. How about the second one?
It's positive too.
Positive. How about the third one?
No correlation.
Oh, no
No
relation.
correlation, right? And then we have some negative, right, or inverse. Inverse. How about this one?
Okay.
It's curved, so non-linear, you see. So the scatter plot actually is a very simple tool, but it can show you very beautiful things on even how, before you even enter the data, you would see so many unique things even about the data before you'd even start. Now, to compute correlation, of course, it's a question, I believe. Does correlation necessarily imply causation? A good question from someone. Anybody? Does correlation necessarily imply causation?
No, it doesn't.
No, it does not. Who is answering? Who is answering? Does correlation
I think it's
imply
the
causation?
regression that implies causality.
Come
The
again.
correl- I'm saying that correlation only tells about the direction, but doesn't implies um, causality.
It
But
does not, right?
regression does.
But what does?
Regression,
Regression definitely does. So the one who asks the question, sometimes you see that if I I cough today, then before the day ends, it rains. I cough, it rains. Another day I cough, it rains. I cough, it rains. There seems to be some association, but that's just association, correlation. And people can actually do research just by checking association as their research objective. But to suggest or to want to know further beyond the association that that's really my coughing impact or cause, that's the word causality, that my coughing cause the rain, obviously it would be a no-no. Correlation, yes, there could be some association there. But because the weather had changed, that's why I most often cough. There could be some association. But the coughing is not causing the rain. So for causality, we need regression to tell you the impact. When it comes to impact, then you are thinking regression. Okay. Correlation, basically association. Now, to compute our correlation, there's a very simple formula that we would often use. I know this analytics class, but let's just look at the formula for theory purposes. Now, rho, which is a correlation coefficient, of course, this is how we measure it. X minus X bar. We know X bar is a what? X bar is a what?
It's a mean.
The mean. So Xi, so every individual value of X, exactly, Douglas, the mean, minus is every individual observation of X minus its mean, Y minus its mean, then all over the square root X minus X bar squared times Y minus Y bar all squared. Just doing this alone should give you the correlation coefficient signified by this variable here, or letter rho. Now, sometimes if you have only X and Y values, X and Y values, you could easily find the correlation coefficient. You don't need to necessarily find the means, just X and Y values. And summation xi, summation x, summation yi, square root of all of this, square root of all of this. It also give you the same correlation coefficient. So you see, this form is useful for hand calculation. Very simple. You don't need to now go around finding the means and subtracting here and there. It's pretty straightforward. Now, but the point is that the Excel or the R or the Python, whichever software you are using, is doing these things in the background. You understand? Using the same formula, nothing more, nothing less. That's what it is. Now, let's see how correlation interpretations would look like. Largely, we know that correlation ranges between what? -1 and what? +1. If you have correlation in the midpoint where correlation is 0, what does it mean if we have rho or correlation coefficient of 0? If you have a correlation coefficient of 0, what does it mean?
It
Yes,
means there is
Asante.
no.
Yes, Asante.
That presupposes there isn't. Yeah, can you hear me?
I can hear you now.
Can you hear me?
I can hear you now.
Hello?
I can hear you. Kindly speak.
Yeah, it presupposes there is. Yeah, it presupposes there isn't any association between or among the variables.
There's no association between them, right? Yeah, so Kingsford Lewis, that's great.
Association between the variables.
Exactly. So there's just no association between the variables under consideration. And you'd see on this spectrum from a perfect correlation to a perfect correlation, we could have the negative extremes. We could equally have the positive extremes. Okay, so yes, -1 means that perfectly inverse. +1, they are positively correlated. So the two go hand perfectly. I don't know. Are there any two things that are perfectly correlated? BMI and weight. Perfectly correlated?
I don't think so. Maybe they are strong, but they are not perfect.
Exactly. Exactly. So, yeah, let's look at a categorization of the correlation spectrum. So we try to give a range so that you know that when it's between here and here, you can say it is weak. Between here and here, you can say it is what? It is moderate. Between here and here, you can say it is strong. And between, say, here and here, you'd say it is what? Perfect. Now, for the most part, you more likely not get a perfect correlation. But perfect is perfect. Perfect is 1 plus 1 or minus 1. And because many things don't exactly go that hand in hand, yes, a range of 0.86 to 1 will be considered near perfect. And so you can put it inside that bracket of perfect correlation. Please mind you, it goes in either way. It could be positive or negative. Okay, so from 0 to minus 0.4, minus 0.4 to minus 0.7, minus 0.7 to minus 0.8, minus 0.8 to minus 1. Once you're in that bracket, you are weakly correlated. Once you're in this bracket, you are strongly correlated. So that was a warmer up. Now, we want to play around some data sets. Do you all have your white wine data?
Yes, please.
Okay. Is it loaded in R yet?
No, please. I'll take some time.
Is it yet loaded in R?
We're not using R, we're using Python.
Sorry,
No,
Python. Is it yet loaded in Python?
About
So,
to.
okay, so if you have your white wine data, kindly load it in Python. I believe we all know how to load that too. Let's do that. So it's interesting how analytics falls everywhere. And this research. So even in wine, whatever industry it is, analytics and data is very important because then it gives you so much information on how to improve not only your product, but also the customer value and your customer base for that matter. So here, this is about wine, data on wine. This wine is the most helpful and most hygienic of beverages. That's just a random quote. Now, we are going to work with some wine data. And if you think about it carefully, you're wondering how wine is coming in to data science. Well, what I've already said, that data science, it permeates all industries, all spheres. The important thing is data. Just to improve what you're doing. Okay. So now this wine, we are saying that we use grape juice. I don't want to go through all of this, but let me just pick up on a few whilst you load your data. So any fruit juice with fermentable sugars can make wine, but grapes being higher on the fruit evolutionary ladder on fermentable sugar content, we choose grapes for making wine. So according to a statistical study, the wine sale estimated to be $39.8 billion and $60 billion around the globe. So you see how somebody's even building this research problem. With this huge cash flowing business, companies are always willing to use technology to elevate their business to the next level. And you think about what is next. So the remarkable power of data science, machine learning, analytics, the company can make use of their data to stay ahead of their competition. It helps executives, directors, managers to understand their business and change strategy, make decisions using a more data-driven approach. Now, of course, originally there are two data sets related to red and white variants of the Portuguese Vinho Verde wine. It's made available by this, and so we are just going to work with the white wine data. Now, modeling wine preferences by data mining from physical chemical properties. In other words, we're looking at the physical properties, right? And also looking at what? The chemical properties. Now, due to privacy and logistics issues, only the physical chemical input. So for our pictures, it's more of the physical chemical properties. Physical chemical properties. And then the output variables are more sensory. So more of perceptions, what you can taste, smell. So the taste of the wine, the smell, and those stuff, the sensory stuff. So they said there is no data about the grape types, for example, the wine selling prices, etc. If there were, would have been a good avenue for further research. So these data sets can be viewed as classification or regression tags based on how you want to go with your research, right? Now also, we are not sure if all input variables are relevant. So it will be interesting to test feature selection methods. So that feature selection methods is to help you know of all the input variables or the features that we have, which of them is contributing more to the quality. Okay, so let's say we have a number of features. Which of them is contributing more to the quality of the wine? Okay, these features that we are testing. Okay, that's basically feature selection. And so this is quite an interesting stuff. Let's look at our variables, as it were. Is there a message somewhere? Okay, there's a test here. Okay, Python, great. Now, if one more is from Cortex et al. 2009. These are our input variables based, of course, on the physical chemical test. We have something on fixed acidity. Now, I don't know if any of you works in the, how do you call it? In the winemaking press or industry. Some of us are data scientists, so, or at least we're in a teaching space, but we play with all kinds of data. So maybe for research purposes, you may have to understand what these variables sometimes mean so that when we're interpreting, we could make better sense, okay, of how they go hand in hand. So one is about fixed acidity. So data was collected on fixed acidity. These are the primary fixed acids found in the wine: tartaric, succinic, citric, malic. I mean, some of you are good scientists, so I know you remember all these things. Now, you also took some data on volatile acidity. So volatile acidity is the gaseous acids. The gaseous acids that is present in the wine. Citric acid, weak organic acid found in citrus fruits naturally. Residual sugar, amount of sugar left after fermentation Not forget, these are your inputs. We want to see which of them contribute more to the quality of our wine. Chlorides, amount of salt present in the wine. Free sulfur dioxide. So that's sulfur dioxide, which is used for prevention of wine by what? Oxidation and microbial spoilage. The total sulfur oxide, this has to do with the free, which is perhaps active, and then the inactive, putting them together, total sulfur dioxide. Then we have density, that's the density of the wine. We have pH, of course, used to check acidity. Then we have data on sulfates. So added sulfites preserve freshness and protect wine from what? Oxidation and bacteria. 11, we have alcohol. So that data of alcohol means the percent of alcohol, that is what? That is present in the wine. We have quality. Now, quality is our output variable. That's our target. Remember, it is scored between what? 0 and 10. What do you think? 0 and 10, is it ordinal or continuous? If you have data that range between 0 and 10, is it ordinal or continuous?
Ordinal, sir.
Yves says ordinal. Okay, any other? Ordinal, it follows a certain order. Beautiful, someone as well. So yes, it's ordinal. And the beautiful thing about this is that even though it is ordinal, regression models would assume it is continuous. So many times when you have ordered data which are more than 5, regression will assume it is continuous and treat it as a regression model. So if it were ordered in a manner which it is, you more likely use classification models, but regression would handle this. The model will handle a regression model because it is more than 5, between 0 and 10. Okay, so you don't necessarily need classification models to handle this. Regression models can actually handle this. Now, white wine, our data set covers 4,800 and what? 4,898 observations. 4,898 observations. We've already suggested that our target is the score, the quality score, which we've already said range between what? 0 and 10. Okay, so it's here. It is ordinal, but often modeled as what? Continuous in regression. That's great. Now, features, 11. So you'd see that from 1, these are our feature variables, 1 through to 11. So you have 11 physical-chemical attributes, and they are all numeric. All numeric simply suggests that we don't really have what? It means we don't have what? It says they're all numeric. It means what don't we have in the data set? Yes, Kingsford.
It means we don't have categorical variables.
Exactly. Exactly, yes, that's great. It simply means that we don't have categorical variables in there. Okay, so strictly numeric. Now, if your data set is strictly numeric like this, sometimes it is good because it's pretty easy. to play around. It's quite easy. You can easily do your correlations using more parametric approaches. Like you can easily run a Spearman, a Pearson correlation because they're numeric. But if it were categorical, some embedded in, you may have to use a Spearman or take out those categorical variables, right? So yeah, so this is a good thing for us. The data set is strictly all numeric, so it may be quite easy to play around with the data. And of course, once you look at the Excel, it suggests same, right? It suggests same. It suggests same. Great. So good thing about this data set, all numeric variables. So like I was saying, no pre-processing headaches. It's real-world relevance, commonly used in regression benchmarks. Now, we want to start from here. So the first code here, of course, is to import our data, which we have as white wine. So we run, and we're going to name it DF. Okay. So we just have that in there. Then view our head of our data. Okay. Of course, we know that the head is giving us the first what? The head is giving us the first 5 rules, if you like, the first 5 observations of our data set. And as you could see, and as you could see, from Excel, these are data. So we just have the head shown in there beautifully for us. Right. Now let's try some data pre-processing. Because many times, data can really be messy. Can really be a mess. And we need to do some pre-processing. Now this pre-processing is very, very helpful many times when you're doing actual research, which most of you will do in your final thesis. Because you could take a lot of data and you notice that some of the data has missing values. In other words, if you have a number of observations, 10 observations, 8 you could get for a particular variable. But for a particular variable, you won't get a data for 2. These are missing values. Or even sometimes for a particular variable, you may not get a number of years worth of data. Why? Because it didn't start collecting data from that point. You see, for even some data, if you are taking maybe daily data, maybe stock price or some other, when it comes to weekends on some variables, they go on break, they don't work. So Saturday and Sunday data, where do you get it from? You don't have. But other variables would have all true. So these things they are always there. As a data analyst, data pre-processing will be a 10. You can't run away from that. And it's a good thing to keep the data more, it makes the data more balanced and more believable when you run your analysis. Other than that, you'll be getting a lot of misleading, unreliable, biased results. Okay. Now, sometimes even depending on how you take the data, you see that there are a lot of duplicates. It could be no fault of the collector. It could be that people have similar values that just duplicates. Okay. And if you keep all of these things, they may unbind data in a manner of way. The system has a way to churn these things out. Another more common issue when it starts with working with your data that you have to be mindful of is outliers. Okay, outliers. Where sometimes you could have very extreme values. Very, very extreme values. Very extreme values. And so by going through this, because these extreme values have a way of impacting the data. For example, think about it this way. We have general, maybe a salary range. A salary range of say, let's say between 5,000 and 7,000. Okay. We take the average, the mean of 5,000 and 7,000 will likely be 6,000, correct? I think that's correct. So it's okay. So the average of the salary of perhaps this class is around 6,000 Ghana cedi. But if there are at least three people, just three people, who are earning, say, 20,000 each, just three people, 20,000. And the bulk of the class, about 50 plus people, are between 5,000 and 7,000. But just three people are making 20,000 Ghana cedi each. You know how to find the mean. You add all and divide by the number that is n. You see that we shift the mean from 6,000 somewhere even around 12,000 or 10,000. Now, if you are not circumspect in the manner in which you take your time to pre-process the data, you just go with the flow, hook, line, and sinker, but results won't be reliable. Okay, so it's better to go through, look out for outliers, and there's very specific things that we most often do to eliminate these outliers, and then to make the data more sense making. Okay, so let's look at a few of them. Now, a very simple thing to start with, I'm sure you know most of these codes already, is df.shape. You'd want to see the number of observations, okay? The number of observations, the entries. We want to do, say, df.info. That should give you this, as you see. So while the shape is telling you the number of entries and the number of columns you'd have, the df.info is now listing out the variables even in the Excel for you. Okay. Now, it also helps you to see whether they are even missing values. I say that we set the data set, the range between what? What are the observations? 4898. Okay. 4898. And see that for all the 12 variables we have, 4898 all across the board. So once I run this, I'm good to go. Okay, of course. Then we have, of course, we know the floats, we know the integer. Integer is between the 1 and 10. The float, we have more decimals in there. I ran a df.describe.t, t doing the transpose for me, rounding off to some 3 decimal points. And we see a very beautiful descriptive statistic like this. A very simple tabular descriptive statistic like this. Many times in your research, some outputs, the way we it's not standard, but when it comes to figures, Python is able to give you figures that when you copy, you paste it inside your Word document, your research you're writing, and it's clean and tidy and very beautiful. And see how this one has giving you that transpose data in a very tidy format. You could easily also pick in from here and then do some writing better in your Word. It just gives an idea of how to organize your work. But what is key here on the descriptive? Who can say something interesting here in this data point if you run yours? Look at something interesting in this descriptive statistics that we have there. Can I see anything interesting worth noting? Yes, Asante.
I think there isn't a missing value. The observations are the same across the observations, the variable.
Right, that's great. Any other? Many times when you have a descriptive statistic, two main things should be of interest to you. You go to your mean, you go to the standard deviation. So for example, fixed acidity, we didn't really know the range, but at least we know the minimum value there is 3.8. The maximum value is 14. Volatile acidity, minimum here is 0 point. Maximum is 1. So we are getting a hint of the range. Citric acid, 0.3, 1 point. Residual sugar, 6.3, 65 points. So you're seeing a very huge range. Chlorides, 0.4, 0.3. Free sulfur, 35, 289. You are seeing something else here. It's giving you hints, the minimum and the maximum. When there's so much gap, the range between the minimums and the maximums, then you should be looking towards your standard deviation. And see whether the standard deviation is high. Because when the minimum and maximum values are so high, or the range is that high, then it means there's so much variability. And the standard deviation value should be able to capture that. That the data is not that normal, is not spreading well across the mean. It is dispersed. It is scattered. It is wide. The range is too wide. So you see, free sulfur 35, maximum 289. That's extreme. Total sulfur 138, maximum 440, quite extreme too. But density 0.9 and 1. That's fine. pH 3.1, 3.8. That's fine. Sulfate 0.4, 1.8 is fine. Alcohol 10.14. The range is beautiful. Quality 5.9 points. So you see, just by looking at this, you could tell that free sulfur and total sulfur, they have very high dispersion. And it's very easy to see, look at the standard deviation. When I scan through the standard deviation column, it is very easy to see free sulfur, total sulfur dioxide. It means that the observations are very dispersed. They are not very close around the mean. Okay, and it was easy to see when we just scanned through the minimum and then the maximum values, the range. You could see that they are so dispersed. And sometimes, depending on the kind of research you are doing, you may have to try to normalize that so that it behaves. You want to bound it Okay, you want to bound them within some ranges. Other than that, if they are too expressly dispersed, it may have an impact on your scores and they may be somewhat unreliable. Okay, so this just gives a hint, a simple descriptive, and we could see this much. But more importantly for us, none of our variables has what? Has missing values. But of course, we could see that some would have what? Outliers. Which of these do you think would likely have outliers? Yes, Asante.
Most likely, the two sulfur dioxides.
The two sulfurs, I agree with you. Because the minimum from one was 35 with a maximum 289. That maximum could be the, how do we call it? Sorry, what is the minimum? So sulfur, free sulfur. The minimum here is 2. In fact, see, let me this. The minimum here is 2. 2 is the minimum. Not the mean, no, the minimum. The maximum is 298. What's the mean? The mean is 35. So this is telling you of what? A likely outlier, right? Total sulfur, 9 is minimum. Mean is 138. Minimum is 9. Maximum is 440. The mean is somewhere here, 138. It's hard to tell whether it is the 9, which is an outlier, or it's the 440, which is an outlier. But I mean, you have to do further checks, and there are so many ways to do those further checks just to know what's happening in there. So yeah, that's about it. As we've already spoken about missing values, okay? Yeah, problem. Yes, Kingsford, please. Kingsford, please go ahead.
Yes, so Sir Godwin, I wanted some clarity. So if you can scroll up a little, would there be an instance? Oh, it's okay. Just the summary statistics. Would
Okay.
there be instances where you can get some data sets where your standard deviation will be greater than your mean? Is that possible?
The
Or
standard
maybe,
deviation is greater than your mean. Yes, it is.
there could be instances where a data set could give you that.
Oh, yes, I've seen data sets where the standard deviation is greater than the mean.
So what would that mean?
Exactly. So in such instances, it means that that very variable, you really need to re-look at it again in two ways. One, to work with it, you may have to think of normalizing it or looking out for outliers. That's basically one of the things that causes it. Outliers. You may be considering some interquartile ranges. Throw the lower values up to 25% off. Values above 75%, throw them off. And then try to thin them between 25 and 75. So you throw lower 25 off, upper 75 off, and thin them. You'd have to, so you see, once you are throwing these away, then now you are creating missing values at some point, which will affect other variables too. Are you aware? So this is one way. Another way is that to use some more non-parametric approaches. Those ones are able to handle some of these data points without any struggle. Okay, so those are the options that you have. Are you okay, sir?
Yes, thank you very much.
Right. Now, even to go ahead, this is just to playing around missing values. There is, how do you call it? A package called missing number, missing no. Now, you can run this. I've already run mine. Missing no. Once you have missing no, you can run this code. The whole idea is that they want to give you a chart. They want to get a chart. Now, this chart this chart, if you look at it carefully, we have the variables on top here. We look here, 1 all the way to 4898. Now, if there should be some missing variable, in fact, you see that all of them are blue and straight. If there were some missing variables in there, you'd see some white lines cutting across, cutting across, cutting across, cutting across, cutting across, cutting across. That will show that, no, check quality. There are some missing values in here, in here, in here, in here. Check volatile acidity. So you see some white lines here, 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 here. To give you a hint on the row number. Check, 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 check. And then you would see that there will be some missing values in there. But for us here, there's nothing. And so it's just straightforward. So you can run this code. Of course, we are given the colors. These are different colors to show if they are missing values. They should just spread in there. So it does, we kind of see that there's no missing data using the missing map, which kind of confirms what we already know, that all the observations have their values in there. Now, another thing we could also do, is to check for normality. Okay, if you want to check for normality, that's a way of pre-processing data, how the data looks, the curvature, either the density of the data, or even perhaps the plot. You use histograms or density just to check how the data looks. So for instance, here, we are running a histogram plot, okay? And this is for regression. Now, for regression in the sense that we are considering our dependent variable, which is quality, okay? And then kernel density plots. Now, because the data sets are extremely large, you see that the kernel doesn't really go over it. Ideally, it should go over this and show you that curvature. You see that curvature. Now, because we are seeing that the dependent variable is 0 and 10, regression will see it like, the model is like a regression model. So it's the kernel density works for continuous data. Okay, and this is what we are seeing. Does it look normally distributed? What do you think?
So it's almost normally distributed.
Yeah, it looks kind of normal, right? And if it
Yeah,
were,
because it's almost bell shaped. But for the fifth bar, it is almost 1,005. I would have just conveniently concluded that it is normally distributed. Maybe you may have to investigate that. That's okay. At least bell shaped.
Exactly. So you could almost tell that it has that bell shapeness. Now, if you're thinking of like a classification, then you won't really be using the histogram. Then you'll be using more of a bar plot. So count plot. So you can run this also. Count plot for the bar. Okay, that's a count plot. So that's a bar chart. But if you assume it is histogram, to see between 0 and 10 for each of them, what are the counts for them? So 0, this is your count. 1, your count. 2, your count. 3, your count. And it still has that baleness, like the gentleman suggested. Okay. Now, beyond the main target variable, you could also do some 1 or 2 checks for your, how do you call it? Your features, which are your predictors. Okay. So are they normal or are they skewed? A very simple code you could likely run is, so df is our data, his bins 25, we want it to be tightly packed, figure size 1010 display, plot show, run. Okay. So we have this. I don't know, but which of these do you think looks a little more normal? So here we're running for just the data df, so everything, both the dependent and the independent all together. Which of these look a little more normally distributed?
Quantity.
I think pH is okay.
I mean quality, sorry.
Quality. What is quality? Okay, we already saw quality as our dependent variable, right? So yeah, that's true. Quality looks
No,
normal.
it's pH. I think quality is the one below, so I think it's the pH. The names are on top.
pH, yeah, pH looks very, very, very quite normally distributed, to be honest. pH. Any other? Free sulfur oxide. What is free sulfur oxide? Free sulfur oxide. Okay, here. Yeah, to an extent. You'd see that the way it is here, you say it is right-tailed. So it's skewed, it's skewed, it's skewed, it's skewed. It's skewed. You see, it's very skewed here. Beyond that, it would have looked quite normal. It's very skewed here. They are not in the center. It's right skewed all of here. See for chlorides, right skewed all of here. And it's right skewed, you see that they move to the left side and all the tail spreads across. The tail spreads across. So okay, total. So all the comment, let me see. Was it total or free? Okay, it says free. Yeah. I prefer total over the free. That looks a little more normal. But I mean, you see that pH does better. Looks more normal. You'd see that maybe total sulfur somewhat looks normal. We have, of course, our quality. Now, give or take. I mean, it's also easy to just test and get numerical value straight away and whether it is normal or not. But just using our eye visuals gives you a general perspective, a general idea. They don't really hit it like that. It is or it is not. But the visuals are very important when you put into your work. It makes the reader follow your work and enjoy your work when you see the visuals and then you put a numeric value that, okay, so this numeric value and this p-value is less than this, so therefore it's not normal. So, oh, okay, so then the picture now makes it easier to appreciate the number. See, it's very easy to appreciate when the graphics are in there. Okay, so let's see if we can detect missing values, which we've been doing for a while now. I mean, another simple code, which most of you already know, is null. Okay, so once you run is null, it just makes a listing of whether there's any missing value in any of these variables. I mean, clearly we knew that there was nothing in there like that. So 0 across. So that saves us with that. Now, there's something also that we call feature engineering. Feature engineering. Now, the whole idea of feature engineering is that with the variables that we have, these variables, you can actually create new variables from them. You see, you can create new variables from them by doing some manipulations, which are very correct and acceptable depending on how you go about it. For instance, you can actually create, and these are all engineering. You see how we have accounting engineering or financial engineering. People are able to manipulate the books, and it is very correct. It's still the professional way, but this is in terms of data, right? But like, so you can create a new feature. For example, if you're going to use ratios to create a new feature, it's about it's engineering. Okay, we are just trying to add features beyond the one you already have in a manner that will improve your model or predict your model better. That's just about it, to make your model more robust. So if you think about it, ratios, that's one way to do this. How? We have acidity ratio, don't we? Oh, we don't have. We have fixed acidity. So yes, fixed acidity, which is a variable. We have volatile acidity, don't we? Volatile acidity. And then now we are creating our own variable. And of course, it's not like we are creating our own thing. It's a ratio that will likely exist. So to create this new model or this new variable into the model, it's as simple as fixed acidity dividing what? The volatile acidity. So for all the data sets, you're just going to do that for you. Create a new one, this over this. You can do that in R very simply. Sometimes you could do binning. Okay, you can just create some categorical variable. Not necessarily categorical, but you break one of the variables, let's say alcohol, into levels. That looks like categories, okay? So low, medium, high. Or you can even do, it's just the same concept, the encoding, where you break them into binaries 0 and 1, or ordinal encodings. Okay, so if you have some categorical variables already, you can just code them into, like how we have our quality. You can just code them from 0 to 10. If you already had it in a categorical data already in some kind of order. So agree, strongly agree, more strongly agree. You can do the encoding in an ordinal way. All these are feature engineering. They're just ways to make the data ready for, or to better do your analysis and improve your model, right? Now, I think still a lot of play arounds. We can detect outliers by doing a simple plot. Of course, to do this plot, you need your matplotlib to be imported. So using a Seaborn code, we have plot.figure size 20 on 5. Of course, I think we can adjust the 20 and the 5 to see how this thing looks for us. So SNS box plot, data plot. So we run this. And then we have our variables, a box plot across all of them. I don't know. Let me change the width here or the height here to say maybe 10, for example. Run. Okay. So then we have some data points. Now, how do you know which variables have extreme outliers? How can you tell that this particular variable has some extreme outliers? Anybody?
By the points below and above the limits.
The point,
Below and above the limits.
the limit. Okay, that's great. By looking at the values that are out range. Thank you, Yves. Yeah, so you're both very right about that. You'd see. So which variables do you think have a lot of outliers? Which three variables would immediately come to mind by looking at this plot?
Free sulfur.
Green, free sulfur. I agree. Any other? Yeah, so Yves says free sulfur. Any other? Residual sugar. I kind of agree. I agree. Any other? Is that one says sulfur, sulfur, sulfur dioxide. Right. Sulfur. So you mean total sulfur dioxide, right? Because I remember us having any variable as sulfur. Do we have sulfur dioxide? No, we have free sulfur, and then we have total. So which of them? Or you mean both of them together is sulfur dioxide? Total, right, exactly. And you can easily see from this, so these are observations, so this single value here is an observation. Now you see the box, the beauty of the box plot is that it shows you where majority of your data is lumped in, with this line giving the median line. Okay, maybe say 150, that's the median line. Majority of your data set is lumped in here. Then it has the limits for the whiskers. Now, once you go beyond these whiskers, means you are out of the range, out. So most of these guys above the 75th percentile, they are just out there. Right from here, you see a lot of outliers. For this one, is worse. Is there. Okay, even see, so even below, because most data points are here. Some are just down there. They're just down there. Some are just down there. And if you see free sulfur 2, yes, there's one very variable. And the many time when you have these outliers, you may likely delete that entire row. So for that observation, you may likely take off the row. Once you're taking off this, it's going to affect all of these variables. You just clean that row off. So you check for all these. This is one way, depending on the kind of data. If you're doing a research where your data is not much, or sometimes outlier is not really a thing like that, you could reserve actually all and work with it. Depends again on the social science or where the kind of research you're doing, how sensitivities to outliers. You see, then you check for all this before you take them out. We see residual sugar also having an extreme value. I mean, for its range, majority are here. So the ones above the whiskers, they are all out there. They are all out there. So I mean, sometimes when you have these outliers, like I said, you may decide not to do anything at all. But sometimes you can actually delete that row. Or sometimes you could actually use some normalization approaches. I think somebody asked a question earlier on what to do. So you could do a normalization approach. A very common one is the z-score, which is very common for normalization, just to keep the data all within a particular range. You bound the data within a particular range, okay? Just so that all those extreme guys will now be bounded. If it's 1.1, 1.2, they can be 1.9, but they're all between 1 and 2. You bound them in there, you see. I mean, beyond that, there are also other things. So this interquartile range, for example, is like, say, the lower 25%, about 75%. All values beyond and below, we just see them. An easy way is to just, there's simple computations you do, and then you just take off these values, which are extreme, so that it just leaves the ones left in there. This box plot histogram, they're just a way to show you which values are going. Scatter plots, I mean, they are easy ways to show you, but they are not really correcting. They're just showing you where these could be. A log transformation is also used a lot in economics and econometrics. Okay, so things like wages, income, GDP. Some countries would have like $1 million GDP. Some will have only 500,000 GDP. The gap is just too wide. When you're working with all these data sets, somebody USA will have maybe $350 billion as GDP. Then a very small country like Togo will have maybe 1 million, something like that. You see, the gap is just too wide. So you normalize them. An easy way is to just take the log transformation. Just do log transformation, and then it bounds them within a particular range. You more likely get a normal distribution. Sometimes you can use very advanced approaches like this one class SVM or this local outlier factor. So what they do is that this SVM will try to learn. It will learn the data. It will create its own boundaries. Okay, this one class SVM to create its own boundaries. So it says that it is learning the pattern. You see that some variables are going extreme, it just cuts them. It flags, it cuts off flags, and then it cuts off flags, and then cuts off. This local outlier is very often used when it comes to clustering. Okay, also a way of identifying outliers. It does a relative comparison using some density stuff, but these are just advanced stuff. But regardless, there should be a way to handle. So what do you do if outliers are there? What? First, understand the outliers. I mean, you can't just be here to say it's an outlier. I've seen the box plot, outlier, delete, delete, delete. You have to understand with respect to the variables with which you are working with, right? So are they errors? You see, sometimes, and some people too. So you have to be typing in there. I don't know if any of you have tried to use SPSS before. So you take data, then you type in, you ask this person, you type in, second person, you type in, third person, type in. So you want to write maybe 5, then write 55. And that 55 can be an outlier because if the range was between 1 and 5, 55 is an extreme value. Okay. Sometimes it could just be an error. So you just have to observe. At least the good thing is the plot hints you that check this, check this. Was it a typo, an entry mistake, or sometimes it could be natural extremes. Okay. So like in our case, very sweet wines or high preservation wines. Sometimes it could be shocks. In some particular years, everything is normal. But in a COVID year, GDP is very low. These are outliers. It defies the regular patterns. So if the average GDP is between this and this, but that very year, it's a shock. Okay. You may have to take out that very variables. Or so you have to understand the outliers first before you go about. So how do they impact your analysis? Yes, they can skew your summaries, like we saw with the means going agog when the outliers are present, or they can actually skew your machine learning models. Emmanuel, are you writing on my screen? Okay, so of course we've seen how to handle these things. Can use standardization and this read last well elastic net. Yes, Emmanuel, please. Emmanuel, can you come? Please speak, Emmanuel.
Hello, can you hear me?
I can hear you clearly.
Okay. For the outliers, when we
Yeah.
talk about COVID-19, we all know that one there, it creates an outlier.
Yes.
But I have something I'm doing that
Yes.
involves the data around the COVID-19.
Okay.
But because I'm taking an average for Windows,
Yeah.
it just it made it look like there's no outlier.
Okay.
So when you look at the exchange rate, let me use exchange rate. For example, within 2022, October
Yeah.
there, it went up to 17 thereabout. But when you take the average from 2 weeks, it doesn't become an outlier. Is that fine when I'm using that one to build a model?
So if you say if you take 2 months, you see it over there.
Like
So if it's 2 weeks,
yes.
are you doing 2 weeks kind of
Yes, because there
moving
are
average, 2 weeks moving averages you are doing?
Yes, because there are two windows. Like petroleum pricing, there are two windows.
Right.
Yes, first window and the second window. Then I'm
Right.
finding that average exchange rate average around that windows.
Right. Yeah, so the question is,
So the question is because I extract an average, it's making the outlier not appear.
okay.
Because there's no outlier during those period. Is
Okay.
it fine we do that in creating the predictive model?
I ask whether the pre-model will still be robust if you go ahead with it.
Yes.
Yes, I mean, so that's why we are saying that sometimes the manner in which you look at the outliers, many time it doesn't mean because it is there in present means that you have to necessarily take it out or not. You would have to observe in relation to the other data sets. If in relation to the other data sets, it is not skewing the data, that's the key thing. You may not even have to do anything about it at all. Once it doesn't seem to skew the data, why not? You do go ahead and work with it. But a better way is if you are doing the 3 weeks or 3 month moving averages, then that one, you know that you are doing short intervals. They now take the whole data as it. So every 2-3 weeks, moving average, 3 weeks, 3 weeks, 3 weeks, 3 weeks, 3 weeks. So it tries to smooth out the data and when you are going along. Okay.
Yeah, thank you very much.
Yeah. But once you look in and see that it's relatively, it doesn't affect much generally. I mean, you don't have to do anything. It's not always the case that you take them off. By extreme ones, you really have to take them off because it affects your mean straight away. Okay, so we have another thing to do is to run a correlation matrix, which we've been started the whole class with. So we can quickly run our correlation matrix. Run. Yeah, and here I do have a correlation matrix. Now, the beautiful thing about this matrix is that it is giving us a number of things. Who can identify those things? So this matrix is giving us a number of things, and really this matrix, I've seen a lot of research papers that have had this matrix directly and put them into their work very beautifully and very succinctly, just like this. It's giving us a number of things. I think we identify two important things it's giving us. At least firstly, it gives us
P-value.
the correlations. Yeah, somebody is speaking. Yes, who spoke?
P-value.
The p-values, yeah. So beyond the rho or the strength, the magnitude, it's also giving us the significance of that correlation. So of course, the manner in which you read it is many times the concentration is on the dependent variable. So I'm down here, quality. Quality. If you look at quality, which three variables in our case seem to correlate highly with quality? Which three variables seem to correlate highly with our dependent, or let me say our target variable? Which three predictors seem to correlate highly with our target? Or not necessarily highly, but relatively, they are the highest of the correlations with the target variable. Which three?
Alcohol is one of them.
Alcohol is definitely one.
Density.
Density is definitely one. Alcohol, density, volatile. What is volatile? Oh, okay, volatile acidity. Yeah. So we already, we started by saying there are some ranges that they are moderately correlated. But what's interesting is that as you see that some of these are kind of weakly correlated, but they are the ones that correlate well with quality. Let's check how significant they are. And you see that they are actually significant. Some are very low, but they are still significant. That's quite interesting. Significant. Significant. It means really they move together. Even though it is slow, but they really do move. It's not by chance. That's the key thing that the hypothesis that is by chance is debunked. Albeit that it is very small, but they do really move together. The association is there. It is significant. Okay. So we have volatile significance. Negative, but it was still significant. You see, this is 0.01, but the p-value clearly was not. Let me ask, which three variables are or show signs. Which two pairs? Give me 3 examples of 2 pairs of variables that show signs of multicollinearity. Three pairs, 3 variables. Or better, so 3 examples of 2 pairs of variables that show multicollinearity. Anybody? Which 2 pairs of variables show high multicollinearity? Alcohol and density. Let's check that. This is density and this is alcohol. Density and alcohol. I agree, sir. Minus 0.78. That's true. Any other? Any other? Which 2 pairs show multicollinearity? Density and residual sugar. Density, residual sugar. What is residual sugar? I perfectly agree with you, sir. That's also very true. Any other 2 pairs that show high multicollinearity? Residual sugar and alcohol. Alcohol and then residual sugar. Yes, not bad. Is there anyone better than that? And I see the number better than that. Okay, so I've seen things like total sulfur and free sulfur, and it makes sense that these two will highly collinear because free sulfur is actually a subset of total sulfur. So you see that they have a pretty high correlation, and that makes sense. So even the color coding helps to identify which of them are perfect. The ones are very dark green, and the ranges, you see, when it comes to the negative, also very high. You'd see with this pink purplish color down there, and so on and so forth. And so once you have this matrix, it's showing the p-values. This could be somebody's research objective, and it's done with that. We just interpret this, speaking to it. When it comes to quality, this like alcohol seems to correlate very highly. Density also, and it's significant. P-value of 0.0, right? Mean less than alpha and all that. And so, yes. And so, given that it is about wine, you may want to connect the statements in such a manner that fits the data. So, for example, alcohol content is inversely proportional to residual sugar. Hence, if sugar content is increased, alcohol quality decreases. So it's just a correlation, not a causality. It is not causing it. One increases, one decreases. When we spoke about multicollinearity, we're talking about 2 predictors that are highly correlated. 2 predictors, not with the dependent, but among themselves. 2 predictors which are highly correlated. Now, as machine learning experts, since it's Python, definitely you're going to do the train test split. So, General, what do you know about the train test split? So, General, what do you know about the train test split? Yes, Kingsford.
Yes, so because the modeling we want to do, we want to ensure that it is generalizable. We prefer that we
Yes.
have some set of data which you split it depending on the rate. Some could do 80-20, some could do 70-30. Use the 70 to test it, and then you introduce the 30%, which is not unseen to the model to try and see if it will do well on the train one, and that will give you an idea if this data model could be generalizable or not. Yeah.
Right. So basically, that's the purpose of the train test. And so since it's machine learning, obviously, the train and test it's a constant thing that we're going to do, because unlike econometrics or regular regression or OLS, where we use all the data and then we just run, when it comes to machine learning, obviously, you have to consider issues of overfit. Okay. And so we don't want to make the data overfit too much on the train. The train data set, I believe you understand the train and the test already. The train data set is like you're going to write an exam, and then you have some study material. So you train yourself with that material, true and poor, over and over. If you've done some class exercises, you go over them so well. You go over the class exercises so well that you know them by heart. You can just be reciting them extempore. It's just in your mind there. You've trained yourself so well. If we allow that, that's going to be overfit, because you know the data. You've seen the patterns in the data. Now, if I bring an unseen data, which is not related to yours, you now struggle, because you've seen the patterns of the trained data so well that it may not work so well. That's an overfit situation. So the way the train validation and test works is just like going to write an examination. The examination is the final one, the test set. So the exams you write it only once. That's a test set. It's used only once at the end to evaluate the model's performance. So you split the data into train and test. But then sometimes you have to include the validation set also. Because, see, if you learn the course material so much, that's a training. You come to know it so well. You write a test. So we use mostly 20% of the data for the test. But sometimes we have to include a validation test to do what we would likely call a hyperparameter tuning. Basically, you are adjusting the knobs, the settings. Are you increasing this a little? Are you reducing this a little? You see? So this is just like a mock. You are doing a mock on a training. You've studied your material story, you know it thoroughly. So do at least a number of mocks, 2, 3, before you come to the final test. You see? So this mock, once you do the first one, then you'd see that, oh, okay, let me adjust this a little. Let me spend more time on this a little more. Okay, so in a tree-based, I don't know if you're used to, or any other regression models, like say the tree-based, you do the hyperparameter tuning. You may want to split the data rather at this point. That's the tuning. Or you may want to see how deep a tree can go. They are all tuning parameters. Okay, it's just a way to improve this. Doing some mocks, the validation does some mocks before we come to the actual unseen data. So we split the data mostly, like you rightly said, the train coming from 60 to 80, the test mostly 10 to 20, validation also some 10 to 20%. We do those splittages and then we are good to go. And if you run a pie chart like this, more often you have, say, if I have 100% data, maybe train will do 70%. Validation of the train, so that helps with hyperparameter tuning because of the patterns. Do the adjustment, then you now do the final unseen data here on the test. You separate some value aside, okay, for the test. So why is this split important, the validation? If we train and evaluate on the same data, the model may memorize the training set, you see, that's overfitting, and perform poorly on new data. We need a way to simulate. That's basically the mock. That is basically the validation. So let's not use the same data of the training. Let's break that one. Let's take a small percentage to validate it, to do the mock. Okay, before we now come to the final test. So why not just train and test? If you only split in train and test, we might tune hyperparameters based on the test. Okay, so indirectly we're fitting to the test. So you're now using the test to do your final validation. So have a small data for its own validation, then now come to the final. So the validation set acts as a proxy, you see that, for the unseen data. Now, there's a question here. Okay, so you guys are saying that there is main data, then there's a test data. The validation is like a mock on the train. Before you now come to the test, why don't you do some mocks so that you adjust your settings a little more before you go to the test? You've done the training, you do a test, but not the final test. So that's in between test is what I'm calling the validation set. Okay, that's like doing a mock. Then when you're able to adjust the parameters better, they now use an unseen data, which is a test data set. Now, this is an unrelated data, please, if you're aware, because we're introducing something here, iris data. This is something on flowers, okay? And the flowers have a number of species. Some are setosa, some are virginica, some are vesicola, you see. So you notice that this is categorical, right? It is categorical. And we have 12 data points from 0 to 12. I'm not going to run this because we don't have this data here. Now, this is just to throw more light on the train, validate, and test. Now, there are so many options you can do. If you code the 0 to 11 and say 1 to 12, so you can first split 60% for train. Is there a question? So, yes, we have some data points here. So, setosa, virginica, vesicola. These are 3 different species of some flowers. Oh, okay, beautiful. So somebody has given us access to the data set. You can run that. But it's just a digression, so I'll just quickly talk about it. So 0 to 11, we have our data points 1 to 12. So we do our first train and then the temporary. So basically the temporary is about, say, the validation and then the test. So if 60% is for the train, then obviously the 40% is left for the temporary splitting to the validation and then the what? The test. Of course, we know the random state 42, so that anytime it is randomly splitting, if I come again, I want to have the same where it did the splitting, the random observations it took, it should give me back those same ones. Other than that, every time it does the splitting, it is random, I'll get different values again. So we fixed that. So we print the train, validation, and test. Now, what this result here means for us is that the original is doing like some 60%. This is our original data, 1 to 12. The train, 60%. This is the random values it took. Validation did 20%. These are the values it took. Test did 20%. These are the values it took. So out of the 12, you'd see this. Of course, there are 12. We are doing 60% of this. That's like 7. So this is 7. You don't expect to get all these being the same, right? So it just does the adjustment. Now, on the same concept of this data set on the iris flowers, depending on how you do the coding, we have the train set. I mean, you can take your time and do 80% of this. There are so many options to consider. But what I really wanted to bring to your attention is this. Sometimes you should be mindful that the way the data is, it is going to be splitting, but you have categories in there. You have categories in there. You don't want to split the data that you have so many setosa in just the train. Then when it comes to validation, it will be only vesicular. Then now come and test on Virginica. The data didn't train anything on Virginica to see how its data points across all variables work. So the model would struggle, overfit all on setosa. Then you bring in Virginica. So it should be a little balance even in the splitting. So it's good to consider even the categorical variables, even as you are doing the split to an extent, okay? So you see. So another example. So when you do the splitting in this example, train 50%, 6 samples, validation, 3 samples, test. You see how they span across. We have each of these sitting across the train, the validation, and even the test. So this is where we do the stratification. It ensures that each class is proportionally represented in all splits. Without it, you might get splits where some classes are missing, you see, in validation, leading to unreliable model performance estimates. And so, yeah. We can just do something for our data here. Luckily, we know that most of our data sets are numeric. Okay, so the issue of classification does not really come in. And then we run that. Once we split, we have our train, 64%, validation, 16%. So we split first into 80 and 20. So the test, that 20% is there. But in the validation, they can under 20% of that. So 80% of 80%. And that gives us this 16%. So, I mean, you can do those kinds of math. Okay. So that helps us with our train and then the validation set. Then you can view just the train data. And yeah. So largely today, this is where we shall bring our class to. If you have general questions, let's hear them before we take a break. And next week, that continues from there. General questions, please. Oh, there's none?
So I just want to thank you for walking us through. I think getting some new levels of understanding as to the things we should look out for. A number of them, but particularly the way you plotted the correlation metrics, and then I think the one before, what's the name of that one? Where you said we should look at, when we look at the describe, we should focus on the mean and standard deviation, and then the minimum and the maximum. Yeah. Sometimes when I go there, I don't know what to look for, but I think that pointer is really helpful. So thank you.
Right. That's great. Welcome there. Okay then. And ladies and gentlemen, you can go back and enjoy your weekends. We talk some other time. Bye then.
Bye.
Bye. Thank you.
Thank you.